Hello everyone, my name is Yonatan Shiferaw and I'm going to present the first part of our work LoRaWAN Class B Multicast Scalability, a work done together with Apoorva, Arora and Fernando Kuipers. And Apoorva Arora will walk us through the next part. Now before we go into the topic, let's set the context. Number of IoT devices are growing massively and some of IoT applications actually need an identical packet to be delivered to multiple devices. For example, here you have a smart street lights where you might want to control a set of street lamps together. Hence, these street lamps might want to share identical packet. Or you can think of smart agriculture, particularly here, for example, smart farm where you have multiple devices that control an actuator. And these two might want to share identical packet. Or we can think of a more versatile solution like Firmware-over-the-Air, where you want to send a firmware update or a security update to multiple devices. And these multiple devices might actually be undergoing to the same update process. So in that sense, you don't want to send the transmission individually in all these applications, because you're going to waste a lot of resources, especially as you increase in number of IoT devices. Hence, multicast comes into play, which allows number of devices to share a single transmission. And this number of devices that share a transmission form a group called multicast group. Now, LoRaWAN has emerged as a popular IoT communication technology. And it basically has three classes of operation. Now, class A only receives downlink after a transmission, hence you cannot control the latency. Therefore, it's not suitable for multicast. And class C is other extreme, which always listen, so suitable for multicast, but it takes a lot of energy, so it's not very suitable for battery-operated device, which IoT devices are mostly. And the last one, class B, is actually somewhere in between, so it listens periodically, so suitable for battery-operated device, but since it's periodically listening, you can also control the latency, hence it's suitable for multicast. So how does LoRaWAN class B achieve this? It transmits beacon every 128 seconds, which can be used to synchronize the devices with the network. And between the beacons, it opens a reception slot called pinch slots with a pinch period, which is actually derived from a parameter called periodicity. So basically, the higher the periodicity, so the higher the period, and the lower the periodicity, the lower the period, and the less frequent slots. And this periodicity is actually known by the network and the in devices. The last important thing is the slot randomization, which actually comes into play in order to avoid the problem that arises from an overlap of slots between multiple multicast groups, which might lead to overhearing and systematic collision. Now, LoRaWAN class B multicast is fairly novel, so it hasn't been carefully studied. So our work tried to fill the gap by studying its scalability in 2 dimensions. So one is try to study the group scalability, what happens as you increase the multicast groups. And the other one is the member scalability, what happens as you increase members. So member scalability, you can read the paper for more details, but it will not be covered in this presentation. So under the group scalability, I will going to walk you through beacon blocking, and Apoorva Arora will take the beacon collision part. So what is beacon blocking first? So gateways are duty cycle limited. That means after every transmission, they have to go to a sleep cycle because of regulations. And this sleep cycle is actually proportional to the transmission airtime. And transmission near the beacon actually could lead to a sleep cycle, which might forbid you from transmitting beacons. Hence, it led to beacon blocking. And we try to analyze this beacon blocking performance using an NS3 module we developed. And it can be accessed in this repository. And we try to simulate this by generating beacons for 2 hours, while trying to make a maximum multicast transmission possible. So we try to do it for different combinations, so for different data rates. So higher data rates means lower airtime, so higher throughput basically. And lower data rate means higher airtime, and so lower throughput. And together with different ping slot periodicity combination, packet size, and number of multicast groups, actually, we try to see what is the performance. And we present the result here selectively in a heat map. So here you see as number of multicast group increase, and here as you see as periodicity increases. And we try to generate the heat map for different data rates. And here one particular thing that you see is as number of multicast groups. It actually results in saturation, which you start experiencing similar beacon blocking. And this actually saturation could be 0% beacon blocking, which is nice here, but it could be as worse as 100% beacon blocking here, since you cannot give any guarantee. The other thing that's quite surprising is you would have expected the lower data rate, which actually have higher airtime, to have a worst beacon blocking. But in this particular circumstance, for example, it's actually performing better than relatively higher data rate. So what's going on here? So let's see it in a picture. So let's say that this one is DR0, lower data rate. And let's say this one is DR1, higher data rate. So what happens is in DR0, a previous transmission has led to a sleep cycle, which is actually proportional with the transmission airtime, which led to a blocking of the ping that would have resulted in beacon blocking. Hence, it's played in your favor. Here, in relatively higher data rate, you had a transmission. However, after the sleep cycle, you still have a duty cycle in order to transmit in the ping that actually led to beacon blocking. So from the result, we can see that we cannot give any guarantee, and it will be the beacon blocking could be as worse as 100%. And actually, all data rates are vulnerable to this, depending on the packet size you are actually transmitting. So we try to implement a solution, and our solution was a lightweight scheduler that tried to avoid beacon blocking. However, it tried to do this while achieving the maximum possible multicast transmission. So to do this, what we actually do is the scheduler actually takes the information about the downlink packets, as well as the information of the particular ping slot. So the ping slot index, ping slot periodicity, and from that, it tried to determine whether it will lead to beacon blocking or not. If it leads to beacon blocking, then it postpones the transmission, and if it will not lead to beacon blocking, then it grants the multicast transmission. So my presentation ends here, and Apoorva Arora will walk us through beacon collision. Thank you.
Hello, I'm Apoorva Arora, and I will be presenting the second part of our study, that is beacon planning in the context of beacon collision avoidance and capacity expansion. Yonatan discussed how duty cycle restrictions on gateways can cause beacon blocking. Following the same argument, beacon transmissions may also result in delayed ping transmissions by pushing the gateways in the off period. Further, simultaneous reception of beacon signals from multiple gateways may result in beacon collisions at the end devices, resulting in beacon reception failure. Hence, we propose an intelligent solution called dynamic region formation for beacon transmission planning to guarantee beacon reception and enable capacity expansion. The idea behind DRF is the clustering of end devices into groups around a single unique gateway. For this purpose, DRF utilizes the average SNR information already collected for the adaptive data rate scheme to associate an end device to its best gateways. So for instance, here in this example, end device E2 would be associated to the gateway G1 and the gateway G2. This is repeated for all end devices, and for this example, we see that we obtain a grouping indicated in this table. The next step is to find the smallest possible subset among the set of the gateways that collectively still covers all the end devices. For this, we use the polynomial time greedy algorithm, which solves the minimum set cover problem that iteratively chooses gateways that contain the largest number of end devices which are still uncovered. After solving the minimum set cover problem, in this example, we see that the gateways G3 and G5 may be deactivated for beaconing while still ensuring that all the end devices are covered for beacon reception. Now, to analyze the performance of DRF, we developed a SymPy-based system-level simulator with multiple gateways, and these were the settings used for the simulations. We compared DRF with beacon randomization algorithm with two settings of beacon transmission probability, p equal to 0.5 and p equal to 0.1. Now we see here from the graph 1 that DRF performs the best by increasing the number of received beacons by 66.52% per end device on an average, with 85% less beacon transmissions as compared to no planning case. So further, in the second graph here, we see the benefit of capacity expansion obtained by DRF by minimizing the number of delayed pings. To conclude, in this study we have investigated in detail LoRaWAN Class B multicast and its scalability properties. In this context, we studied the issues of beacon blocking, beacon collisions, delayed pings, and proposed novel solutions to mitigate these issues effectively. Thank you.